It's a real pleasure to announce the speaker of today. So it's Atsuhide Ishida from Tokyo University, and he is going to talk about Mourre estimate for non-local Schrödinger operators.
Okay, thank you for my introduction, and I want to say thank you very much again to organizers for giving me this chance to talk here. And this is my first visit to Cambridge University, and this overseas topic is first time in 2 years. Okay, in my talk today, we consider the Mourre estimate for non-local Schrödinger operators and expose the properties of the eigenvalues. Then my talk is joint work with and Hungarian Academic Sciences, and Italian Okay. Let me start my from introduction. In 1981, the strong abstract method to study the spectrum of self-adjoint operator was invented by Eric Mourre. H is the self-adjoint operator. Acting on a Hilbert space, and which we want to investigate its spectrum. For example, the Schrödinger operator. A is also adjoint. And Mourre here shown in his paper that A, the intersection of the domain of H and the domain of A is called H, and B E of I theta A leaves the domain of H invalid for theta equals the root value is less than 1, and the sublime of the following. Is finite for E5 in domain H. How do we use this? J. The commutator of H and A defined in the home sense of the intersection of the domain H and domain A in bounded below. And close. And the third joint operator associated to its closed extension specified the following the domain group. And finally, D. There is positive constants G and delta, and compact operator K. The following Mourre inequality. Where E of E sub calculate the spectral projection of H and I is the open Z to under these conditions, one of the most important theorem in the Mourre is if the condition from then the Pierre spectrum of A in the open interval is finite. And he called self-joint operator A conjugate. I will give the simple example.
May I ask you a question? This lambda you fix,
Yes,
it's not an eigenvalue of A, it's just any real number or because
yes. In this setting, lambda is lambda will be.
because this I was this interval from lambda minus f lambda plus f, but this has nothing to do with A. So it's a,
Yes.
so it has nothing to do with A.
Yes.
Okay.
First example is A0 divided minus the fraction over 2 2. As you know, the domain of this operator H2 solve this with order 2. And in this case, we can choose conjugate operator A as the generator of direction, where P is of course the Mourre operator. Okay, let us check the conditions from A to D. A. The rapid decreasing function space S just class is included in intersection of H2 and of course S is that's all. It's there. D. The Fourier transform is the function perfect. Yes. This is equation imperator. The invariant property. And the sigma of is known. Of is fine. Of course, the bracket of X X as the standard square root of 1 plus square. G the data of X and A is we can compute this computed directly. Is X of S. So the cross function of this data is also X squared. And finally, D. For the given positive lambda, we can choose the delta between 0 and lambda. Delta. Delta. And in this case, the Mourre inequality has foreign shape. This commutator is H0, so delta in this case, Mourre inequality holds without compact operator K. However, we already know that this operator, the free-Schrödinger operator, this operator is absolutely continuous, and this does not have any eigenvalues. So the next example is the standard Schrödinger operator H. Sum of minus Laplacian over 2 and the potential function B. Where this function B is and belongs to C1 and satisfies following condition. The power of epsilon minus K with and the length of matrix beta is less than or equal to 1. Okay, even in this case, we can check the conditions from A to D easily. In particular, the commutator is minus x. So, and this function goes to 0 as the x tends to infinity. Because dot this function. So the compact operator K, which has the following shape. Operator is compact. These two examples are associated with the standard Laplacian, and there are a lot of studies on pure point spectrum. On the other hand, what about what general H0? This topic is Mourre inequality conjugate operator A, which is the operator of status and non-local Schrödinger operator. That is the function of Laplacian. I have one remark here. In the Mourre paper in 1981, he also treated this kind of the generalized non-local differential operator, but he adopted the much more complicated pseudo-differential operator as a conjugate operator. One of the aims of my talk is proving the Mourre inequality in non-local case and studying the point spectrum by using this standard conjugate operator A to generate out dilation. Section. Function psi increasing from here. H0 is defined by psi of p squared over 2, which is and H sum of H0 and 0 potential function B. The assumption I will give later. Under the assumption I will give later, this operator is self-adjoint acting on L2. Assumption. A1 function psi belongs to C1 non-negative, and it is also non-negative, and right-hand limit to 0 is equal to 0. There exists positive constants C1 and B1 such that square root of U is less than or equal to C1 and U B1 for non-negative for all non-negative U. And 3. There exists positive constant C2 such that U diagram of U is less than or equal to C2 of U for all non-negative U. F4 and there exists positive constant V. Right? U is greater than or equal to U. Finally, F5 potential function B is their value. And bracket X is H0 relatively common. here there are some remarks. Point 2. Assumption A5 implies that H is symmetry acting on L2. Of course, Catonelli's theorem under assumptions A1 and A2, and A5, the spectrum of H0 is absolutely continuous. Correspond with a real line. And moreover, the essential spectrum of H is essential spectrum of H0 is also a real line. This statement is shown by the wireframe. Next is the first main result in my talk. If assumptions A1 is 5, then the Platonic spectrum of H, except for Z, is finite, discrete. And the multiplicity is unknown. And moreover, the only accumulation point on the spectrum of A, and yes, there. Okay. I will give the key computation to prove this theorem. The commutator of H0 and L in this case is psi of squared over 2 squared. We can compute this commutator directly. Under the assumption A5, under the assumption, this assumption A5, the potential function B is not always differential. But the extended semi-joint operator can be defined from the domain of H to its dual space. This details of this extension of the commutator is stated in page 0. In 1981. I here only note that the assumption A2 is used here. Yeah. I will give that some examples regarding this domain.
May I ask a question?
Okay.
Your conditions on B must be somehow related to psi. I missed this in your conditions. Because you say it's not always differentiable, so you mean this may be only factorial differentiable or something like this. What do you mean? There must be some connection between B and psi, right?
Yeah,
In your condition.
Connection B and
B,
psi.
the potential, and
There's
psi.
a psi. Psi.
Yes, and psi. Because you assume it's H0 compact. Okay, there's the connection.
Oh, yeah, yes.
Okay. Sorry.
Okay, and the first example is that generalized massive relative Schrödinger operator. Right? Plus n plus n to the power of 3 alpha over 2 minus n with alpha, which is greater than 1, greater than or equal to 1, and less than or equal to 2. We can check this function psi satisfies the assumption from F1 to F4. Okay. Indeed, it's alpha u plus alpha this term is non-negative because alpha is less than or equal to 2. Okay, so it is alpha. This implies that assumption F4 holds. And about the potential function, X B belongs to M3 with 2, which is equal to 2 if dimension n is less than 2 alpha and Q is greater than over alpha if n is greater than or equal to 2 alpha. Under this assumption of the potential function B is satisfied A prime. And 2.3 holes. Okay. And next example. Five is the fractional Laplacian. Psi of u is 2u to the power of alpha plus 2 with alpha which is greater than or equal to 1. In this assumption, this restriction alpha is greater than or equal to 1. This restriction comes from the assumption A2. On the other hand, this upper bound alpha has to be less than or equal to 2. This upper bound comes from this positivity, non-negativity. And this restriction from below, alpha has to be greater than or equal to 1. This also comes from the assumption A2. And about the potential function B, in this case, we assume that same assumption. For example, 2.4 here. Then 2.3 also holds. Next, we consider the smooth potential function. If we assume that the potential function is smooth, in this case, we can remove the restriction of alpha from below. And this one. Right, 6. If I put the real value belongs to C1 and satisfies minus that which is positive and the length of maximum beta is less than or equal to 1. If potential function satisfies the assumption Fi prime, clearly its potential function B is relatively compact. And H is separate joint by Cauchy theorem. There is a one remark. function A1 only. The spectrum of H0 is a closed interval there and this is if this limit higher and the spectrum of H0 is that if this limit is 18. Next term is the second main result is of 2.8. If stones A1 A3 A4 and A5 branch, then the pure point spectrum of A, except for 0 and into is discrete. And the multiplicity is higher. And moreover, the only accumulation point spectrum of A can be added. 0 and position 5. I will give the examples regarding this domain. Example is massive relativistic Schrödinger operator with alpha which is positive and epsilon equal to 2 and is positive. Second example is fractional differential. With alpha which is just positive. And potential function B satisfied. Right. Then, right. Okay. Today's talk is in. My talk is in. One, two, 09. Sorry. Thank you. 109. 0154. In the Mourre's paper in 1981, he proved that the singular continuous spectrum of the self-contributed operator is empty. In our archives paper, we also discussed if psi belongs to C2 and potential function B is also C2 function. Of course, we will react and satisfy positive. And the length of the multi-index beta is less than or equal to 2. Then the singular continuous spectrum of empty. By applying the limiting absorption principle. And in our archives paper, we also give some examples of the potential functions such that there are not any embedded eigenvalues. Okay. Okay, that's all. Thank you very much for your attention.
Yeah, thank you very much for this very interesting talk. Are there any questions or comments? Maybe first from the floor.
I have one short question. So it seems that your assumptions on this function psi, basically this is, so I'm interested, your examples are all Bernstein functions.
Mm-hmm.
Do you have, based on certain range of factors, do you have any examples which are not Bernstein functions and satisfy your assumption? Or something that you consider?
Yeah.
Or what would be the best?
Yes, based on considering this talk, we want to study the massive case.
And this, yeah.
Yes, massive case.
Okay, so these are basically some minimal conditions under which you can, yes.
Are there any more questions? So, for people joining us via Zoom, if you have a question, just raise your hand or just start speaking. There's no hand. I have a question which is sort of related to what you've been asking. So, in principle, one can do this without, if you don't think about the perturbation as zero perturbation, you can look at size of more general type. of course, yeah, when you take psi of minus the Laplacian, for instance, using a Bernstein function. So my question is, so one reason why one looks at this framework of Bernstein functions is that you somehow pretend the maximum principle. So at the end, the corresponding real semigroup, not the unit, the real one, has a property called positivity to reserve. So if you start with the heat equation and it stays positive. So my question is, now in your case, natural object is the ground state. Yeah, so you get your free Schrödinger operator, you apply psi, okay, and then the question is, does it have a ground state or not? When you add a V, again, does it have a ground state or not? So in principle, one can think of the Schrödinger transformation. So you divide by the ground state and multiply. So some people call it a transformation error. So in the end, you end up with an L2 space with the weight doing this kind of transformation. So, and then sometimes the first order Schrödinger goes into, sorry, second plus zero order goes into second plus first order operator. So in principle, so you could take advantage of this second picture after dividing by the ground state. And because if these are the Bernstein functions, as far as I can judge so quickly, so that means ground state will be positive. Yeah, at least after adding a constant, maybe the operator will be positive. So really, you can divide, and you get some weighted L2 space. Yeah? So my question now: would your theory concerning the spectrum maybe get some additional results by looking at the ground state operator, study the spectrum there, and then do back the unitary transformation? You get spectral information about the original operator. So there's basically a Schrödinger world on the other side of the picture. Yeah? And I think it would be very interesting, to use this kind of transformation to compare the one picture and the other picture. In particular, there is a lot of techniques once you are in the Schrödinger picture, for instance, to exclude essential spectrum. Yeah? These are the so-called super Poincare inequalities they can use in that on the other side of the world, in the Schrödinger world. And I think it would be very interesting to compare your results under this transformation with, maybe there are no other the same results, I don't think anyone proved, but just to see whether there are additional tools on that side, like a super Poincare inequality and so on, to get information about, for instance, the essential spectrum. So it's more remarkable question. So I think there's a very interesting parallel world that one can study in this situation.
Thank you.
Definitely. Okay, are there any other questions or comments? Okay, then I'll check again, maybe at this.
Hello, Michael.
Hi, Joseph. Go ahead if you have a question. Or
Hello, I'm Joseph. Yes, you can't see me, but I think that you can hear me. So first of all, I'd like to say that Atsuhide's talk was very, very good. And obviously, he had no time to discuss some other aspects. Here, the main point really in this work is to prove that there are no embedded eigenvalues. So therefore, what you have to see is that 0 is a special value in the spectrum, because this is the edge of the continuous or the essential spectrum. So what we were interested in was if there is any spectrum point above 0 or including 0, which is an eigenvalue at the same time. So one of these so-called embedded eigenvalues. This is an old question going back to Neumann and Wigner in 1928, actually, where they have proven that if you if you choose your V, your potential, in a particular very careful way, then you can really produce an eigenvalue. In their case, it was equal to 1, so it was well above 0. And for non-local operators, for non-local Schrödinger operators, in a different work, in a work which is complementing this one, we have been able to produce many examples for non-local Schrödinger operators, where you would take H0 to be, for example, the fractional Laplace operator or the relativistic Laplacian, and you can produce really positive, strictly positive or 0 eigenvalues. So all this Mourre theory business is really about proving that there exists no such eigenvalues, because it has a lot of interest, it has a lot of consequences, for example, about the existence of time operators and some other things, some Strichhart's estimates and that type of business, which of course we did not have time now to discuss. Atsuhide had no time now to discuss. But what I'm trying to say is that this is the other side of the coin in relation to the existence of positive eigenvalues. And what Michael was saying, I think, was really about negative eigenvalues, where you do have a ground state belonging to a particular negative eigenvalue, which is, of course, very, very interesting on its own, but I think it is a different part of the spectrum. What Atsuhide was discussing is what happens when you are looking above zero or at zero and try to rule out possible nuisances which come with positive eigenvalues. Thank you so much. This was just a comment.
Thank you.
Yeah, thank you very much. This clarifies for me the picture. So here's a very particular goal that you're not interested just in spectral information, but this particular goal you're looking at. Now I understand, of course, if the lowest, the lower end of the spectrum is, if there is a ground state, it's completely different direction of questions. Okay, so sorry about my remark, but I just had this association, but I think it is clarified.
Yes, and I want to add some remarks. Okay, as you say, that in these two cases, zero is very delicate. So, and in our paper, we discuss also there is whether the eigenvalue or not. And give the complete example of the basic function.
Okay, thank you very much. So let us thank the speaker again. That's very interesting.
Thank you so much.